Hello, I welcome you to the next tutorial video on microwave-based non-destructive testing. Today we will learn a method for the three-dimensional localization of defects. In the last tutorial video, we saw a method for the two-dimensional display of test results. In that method, the defects are projected to the surface of the device under test. The results in that method are generated by using a microwave with constant frequency, the so-called CW mode for continuous wave. That was also the basis for the earlier videos we had seen in this series. To a very limited amount, that method can also be used to give some depth information of the defects, but that is not rigorous. A rigorous method to get three-dimensional information about the localization of the defect is the so-called frequency modulated continuous wave radar method, for short FMCW radar. In this method, the transmitted microwave frequency is not constant, but it is increased continuously within a certain time interval. The data evaluation relies on the difference between the momentary transmit and receive frequency. This difference occurs because of the propagation delay of the wave between antenna, defect, and back again to the antenna. Let's look to a graphic to explain that. Here we have a block diagram of the FMCW system. This is the frequency generator. Mostly it's a voltage controlled oscillator, for short VCO. The generated frequency Ft can be seen in this diagram frequency over time, and it is increasing over a certain time interval and then starts again, so it is in a sawtooth type. This generated frequency is led to a so-called power divider, where a small part of the power is extracted and given to the evaluation box as a kind of reference signal. The main part of the power is given to the antenna, but not directly, but via such a device which is called a circulator. The circulator is a 3-port device with the following property. At an input port, from an input port, the signal is only transferred to the port which is next in the arrow direction. It is not transferred to the remaining port. So in this case, the receiving port, that is this, is isolated from the transmitted port. In this way, the signal Ft is transferred to the antenna, which radiates the signal into the device under test. A part of the signal hits the defect. The defect in general has a different permittivity than the surrounding device under test. So reflections occur, and part of these reflections also hit the antenna again and are received here. Then they are led to the evaluation box via the circulator.
The defect
is located at a certain depth. So the microwave has to travel from the antenna to the defect and back again. There's a certain propagation delay. So the received frequency is somewhat older than the momentary generated frequency ft. We can see it here in this diagram. The green frequency fr, somewhat lower than the red one. And this difference in the frequency is evaluated in the evaluation box. And the output of it is proportional to the delay delta t, and that in turn is proportional to the depth d, which is the third dimension we are looking for. In the evaluation box also the amplitude is evaluated and gives an output signal which is proportional to the strength of the defect. Lastly, the antenna is moved in X and Y direction. So, in addition to the strength information, a three-dimensional knowledge of the location is obtained. Here we see a mobile version of an FMCW system. It operates at 100 GHz. The test head is moved over the surface of a wind power rotor blade, and the results are shown on a nearby laptop. In the following, we will see FMCW test results of a sandwich from polyurethane foam, 30 mm thick, and two laminates from glass fiber reinforced plastic, each 5 mm thick. Here we see the cross-sectional view. The used frequencies are around 100 GHz. And here on the left-hand side, we see a so-called B-scan. In this presentation, the data are collected from scanning along a line, say along X. The color in the presentation represents the strength of the reflections. The depth of the reflection is shown vertically, and the exposition horizontally. The first strong reflection occurs when the microwave coming from air hits the first GRP laminate. There are strong differences in permittivity, that is 1 and 4.7 generates the strong reflection with the bright color here in the B scan. The second reflection is from the permittivity difference between the GRP laminate and the PU foam at a depth of 5 millimeters. Then at a depth of 35 millimeters we have the reflections from the interface PU foam to GRP laminate. And then the fourth reflection is from the GRP laminate to air again. Well, although the magnitude of the permittivity differences here at the bottom is the same as here in the top, the reflection is somewhat fainter than there. That is because of the following reason. The incident microwave has suffered loss when after this propagation to here, and so it is weaker, and so also the reflection is weaker, and therefore this indication here is weaker. In the next slide we see the results from scanning along a multiple of lines in parallel. The bottom view is the B scan which we have seen before. In the top scan, all the reflection results are presented, which are generated in a depth of 3 millimeters. 3 millimeters, that is within the first GRP plate. And this display is in a rectangle of 600 millimeter times 250 millimeter. This kind of presentation is called a C-scan. The orientations of the glass fibers can well be recognized. And here is the dashed line, which indicates the line at which the B scan here below is taken. The next C scan is here generated at a depth approximately 10 millimeter below the surface, that is within the PU foam. Interesting are the small dots which we can see here. They show the cross sections of small distance rods between the GRP plates, which are inserted to increase the stability of the sandwich. The next C-scan shows the reflections from a depth at 35 millimeters. That is exactly the interface between foam and the lower GRP plate. We should know that the single layers of the sandwich are glued together with an adhesive. And this small indication which we see here shows missing adhesive and a patch of about 20 millimeter diameter.
We have seen an impressive example what microwave testing with FMCW can do. In the next tutorial video, we will see another example. I want to make a comment. We have seen the results which were generated by a 100 gigahertz system. That means the frequency was varied around 100 gigahertz, in this case from 60 gigahertz to 110 gigahertz. A typical 300 gigahertz system would use a span from 230 gigahertz to 320 gigahertz, for example. Such large frequency spans of 50 gigahertz or even 90 gigahertz are only available when using such very high frequencies of 100 gigahertz or higher. That is, waves with wavelengths of 3 millimeter or less. Such large frequency spans are necessary to achieve a good spatial resolution. That's it for today. Thank you for watching. See you next time. Goodbye.